First of all, of course, I would like to thank the organizers for giving me the opportunity to present some of our recent results. So, as mentioned, I want to talk about electronic squeezing of pumped phonons and how we believe this can provide a mechanism for attractive, so negative interactions, and thus in the right parameter regime, transient superconductivity. Okay, so this was joint work with Eli Wilner, David Reichman, and Andy MILLIS from Columbia, and you can find all the details in this recent publication here if you're interested. So I'm in the fortunate position where Andrea already gave his excellent talk on this potassium-3 C60 material, where they report possible light-induced superconductivity at very high temperature. And to just recap, what happens is the experimentalists shine a laser light, which is modeled like this here in this little cartoon, onto these buckyballs, and they tune the frequency of this light in a particular way to one of the phonon frequencies. So when the light is absorbed by the buckyball, it excites a particular vibration. This is actually one of the vibrations that is excited. And the buckyball starts to shake. And now one can report the optical properties of this system after excitation via light and compare that to the equilibrium result. So this is a plot that you just saw in the previous talk. I just stole this from the paper here. So what you see is it's kind of small. So this is the reflectivity independency of omega. This is the real and the imaginary part of the optical conductivity. So sigma 1 and sigma 2, also independency of the frequency. And the red line is the equilibrium result. So the reflectivity in the equilibrium result here saturates to a value well below 1, and that is because you are at 100 Kelvin. This is the base temperature is 100 Kelvin in these plots, and that is far above the equilibrium superconducting temperature, which is about 20 Kelvin in this material. Accordingly, the real part saturates to some finite value, and also the imaginary part goes to this constant here and would turn back down. So this is just in accordance to the Drude model, basically, and it's a normal metal. And that's because you are above the equilibrium superconducting temperature. Now, let's say we excite the crystal first and then measure again. Now you see that at 100 Kelvin, the reflectivity saturates to a value that is almost perfectly unity. And if you translate that, so this is the old data, because I didn't have the new data, you see that there's like this optical gap in the real part of the conductivity. And in the imaginary part, there is this divergence here that is consistent with a 1 over omega divergence, which is the hallmark of a superconductor in this data. So this is, of course, quite exciting because this is at 100 Kelvin, so 5 times the equilibrium superconducting temperature. And in this talk, I want to talk about how one possible mechanism, how you can go from exciting via light, so exciting phonons via light, to these changes in the electronic properties, that is the induction of superconducting properties in this material. It's one particularly interesting thing about this particular excitation that is done in this experiment is that due to symmetry, you're not allowed to couple linearly between the electron density and the phonons. So you're not allowed to couple due to symmetry the oscillator coordinate q to the electron density, let's call that n. But of course, you could couple, for example, to the gradient in the density. But these couplings are usually very weak, and thus people looked at nonlinear couplings. And that basically gave rise to the field of nonlinear phononics. In this buckyball, you have a whole zoo of different phonon modes. It's a quite complicated molecule, so you can have all kinds of phonons. And here is a non-exhaustive list of different theoretical proposals. I also put this very new proposal down here. It has nothing to do with phonons. I just wanted to put it up there so that you know. Don't be fooled by the title here. It's just a disclaimer that this doesn't really fit into this list under this regard. Sadly, I don't really have time to talk a lot about these different ideas. What we want to propose here is to concentrate also on the phonon energetics. So all of these proposals have a common ground that they basically discuss the changes induced by the phonon by looking directly at the electronic properties, so the change in distribution function or the changes in the electron or electron-phonon Hamiltonian. And here we want to add to this discussion basically the question of how does the presence of the electrons affect the phonon energetics, and can that at least partially be a reason how you can explain this mechanism of light-induced superconductivity. So for us, we want to look at a very simple model of a coupling that is symmetry allowed. So let's look at an electron-phonon coupling that looks like this. So you take the oscillator coordinate q and you square it and you couple it to the electron density. This is, of course, symmetry allowed. The only thing that's symmetry forbidden is if you would have a linear coupling. So Ni, Qi is not allowed, but this type of coupling, in principle, you can have. And if you try to estimate this dimensionless constant g here, you find that it's about 5 to 10%. So it's quite small, but maybe we asked basically the question whether in this pumped setup, although this constant g is small itself, maybe the interplay of pumping and this small parameter can lead to sizable effects. And what this coupling means physically is that your restoring force of the oscillator depends on the electron density. So to understand this last sentence, let's look at the, let's say, full Hamiltonian. So we also write down the electronic part and the phononic part that we want to consider. So, of course, in addition to this electron-phonon part that I just discussed. And if you look at the bare phonon Hamiltonian, we model this just by a harmonic oscillator. In first quantization, this, of course, looks like this. Or if you like second quantization better, you can introduce these annihilation and creation operators, B dagger and B, and rewrite this in this nice convenient form. And now if you, for the second, treat this electronic operator Ni just as a number, so we forget for the moment about quantum fluctuations in this operator Ni, then of course you could add this term here to this term, and what you find is a change in the oscillator stiffness. So instead of having k, you now have a new oscillator stiffness k prime, which is just this factor 1 plus 2g times Ni larger. Now, if you change the oscillator stiffness without an according change in the oscillator mass, just think about a spring a mass connected to a spring. If you change the stiffness and you don't change the mass accordingly, of course you change the frequency of this oscillator, and that is just a modification of the frequency via the square root of the same factor 1 plus 2g times n. Now let's come back to the consequences for the phonon energetics due to this shift in oscillator frequency. So let's suppose we are in the mth eigenstate. Somehow we're magically in this mth eigenstate, and still in this simple consideration, the electrons are basically frozen. So it's just numbers, right? We still don't have electron fluctuations. And we ask, okay, the energy of the mth eigenstate in the harmonic oscillator is just given by omega naught times m plus 1/2. And this omega naught, of course, now gets this dependency on the electron density. And now you might ask, what is the electron pairing energy? So that's the energy that you gain or lose if you have 2 electrons and 0 electrons on your lattice instead of having 1 electron everywhere. This energy is just, well, having 2 electrons plus 0 electrons minus twice the energy of having 1 electron in the system. So that's basically the question, do I like to have pairs of 2 and 0, or do I like to have 1 everywhere? Now, if you plug in this E here for this different number of electrons, the effective electron pairing energy is, of course, just the bare, usually repulsive part. So that's the energy that you pay when you try to put 2 electrons on top of each other. And then there's this modification, m plus 1/2 times omega naught, where now this omega naught is the unchanged frequency here. And then from this term, you get, for n equals 2, you get this. For n equals 0, you get, of course, this, minus this twice of this n being 1 here. And now due to the concavity of the square root, these 2 terms in sum are always smaller than this guy. And therefore, this term is always negative. Okay? And you can see this explicitly if you expand to order g squared then you get an explicit minus sign here. You get this proportionality factor m plus 1/2, and you get the leading dependency in G squared. Okay, so this is basically, in a very simple picture, what we propose as the mechanism that basically effectively induces attractive interactions. But of course, this was in a very simple picture. We have forgotten completely about electron density fluctuations and so on. And to study this more systematically, of course, we should write down a model also for the electrons. And what we studied is basically a Hubbard model where we add also the optical phonon mode. So we start out with the Hubbard model. These are these two terms here. So the first term allows electrons on a lattice to hop from site I to site j with hopping amplitude j. And then there is the electron repulsion that is just given by U electronic. And then we add to this Hubbard model this optical phonon mode, which is just a harmonic oscillator, and this coupling that we like via the oscillator coordinate squared to the density of the electrons. Okay, so now treating this model, of course, is quite difficult. And to make progress, we basically took a look at the literature and tried to be inspired by the more usually studied case of linear coupling. So if you wouldn't have this square here, this would be just the Hubbard-Holstein model, and this has been studied extensively in the literature. And one of the go-to responses when you have this model is trying to find a unitary transformation that gets rid of this explicit coupling and basically moves it somewhere else. And this explicit unitary transformation is the so-called Lang-Fürsow transformation. So we try to do something similar and find a unitary transformation that gets rid of this explicit coupling term here. And this is the transformation that does this for you is the squeezing transformation. I give the mathematical details here. I don't want to spend much time on this. But what this does is this unitary transformation maps your Hamiltonian to a new effective Hamiltonian where you now have modified hoppings J star. And you naturally get out this frequency modification in this new phonon modes beta. Now, don't be fooled. This J star here, I wrote this conveniently as just a single symbol, is quite complicated. Just as in the Lang-Fürsow case, you have phonon operators and electron operators in this J. So it's not a scalar, it's an operator. That's just like in the usual case, and this will make life quite difficult. If this would be a number, of course, this would be quite easy because, let's say this is a number, then b dagger b is just a constant of the motion, right? There's no term that would raise or lower the total number of phonons that I have, and then if this was a number, then it would be quite easy to solve because I could exploit that constant of the motion. Okay, so let's get back to that complicated term later and look at this simple term first. So this is the simple modification of the frequency. And if you expand that to quadratic order in the coupling G, you get 3 contributions. The first, so the 0th order, just restores the phonon that you started out with. And then starting in linear order, you get this on-site potential term. So if b dagger b here would be just a number, then of course this would just be a global shift of your energy levels, and you could gauge that away. So that would be actually irrelevant. But in general, if you, let's say, allow for the reduced density matrix of the phonons to be in a mixed ensemble of states, then of course on one side you could pick one wave function out of this ensemble, and on another side you could pick up another wave function out of this ensemble with different number of phonons here, and this would lead to side-to-side fluctuations in your system. And then, of course, we also reproduce this quadratic order term that couples basically to the electron interaction. It's always negative because all of these terms are positive here, and it relates to the number of phonons that you have in your system because it's proportional to this equation here. Okay, so now let's go back to this complicated hopping term and what to do with it. So this complicated hopping term that was written in red on the previous slide looks like this. So now here, this j is really just a number, and these are just the hopping operators. But you see these exponentials that involve complicated bosonic operators. So just as in the Lang-Firsov case, now you're hopping, when you hop from one side to the other with your electrons, you can actually emit or absorb pairs of phonons. So if you expand these exponentials, you will have two types of processes here. The one is an elastic type, so when you just expand this exponential with these boson operators in the exponent, you will get certain contributions that conserve the number of bosons, so you get just the same numbers of B daggers as B. These are easy to treat, but then there are also the more complicated terms that will raise or lower the number of phonons that you have. We call these inelastic contributions, and these will mix and mix up your phonon states so that B dagger B is not a constant of the motion anymore, and this is what actually makes this theoretical treatment difficult. So our strategy now was to go into an exactly solvable limit and devise approximations in that exactly solvable limit, and assuming that these same approximations work in the infinite crystal, use those approximations also in that infinite case. So in this exactly solvable limit that we take is just a limit of very, very small system size. So we just take a two-side version of this model where you can just use exact diagonalization to describe the physics exactly. And then in this two-side model, we employ approximations and check that these approximations are valid. So for this part, we model the influence of the light field, which puts the phonons into your system, just under the assumption that for the duration of the pump, you don't couple to the electrons. If you assume that, then you just put your system into a coherent state. So your phonons are now in a coherent state that looks on each side the same, and this is just a coherent state here. And now if you build the reduced density matrix out of this single state, you of course just get this double sum here, which includes all off-diagonal contributions in the number eigenbases m and n prime. And what we found to a good approximation in this two-side model is that the effect of the inelastic terms can be modeled quite accurately by just dephasing this ensemble. So instead of using this with all the off-diagonal terms in the number eigenbases, we use this dephased version of it. So we throw away the off-diagonal terms. This takes care of the inelastic terms to some approximation, of course. And the elastic contributions, so the ones that conserve the number of bosons, we can write in an effective band narrowing. So now the J star is easy to treat. So this is our new J star, where this band narrowing here just depends on the total number of bosons. So NB is just B dagger B. So B dagger B is still a constant of the motion. Yes?
Doesn't it introduce disorder, a lot of disorder into your model, into this effective model, both one side and the hopping and
this mix?
The transforming sounds like it will be more disordered. You look at the snapshot of your Phonon system, and then you normalize your parameters. It's cool to just making your model disordered. Is it correct or not?
Yeah, so this basically goes back to this term here, right? So you're talking about things like this. So here I said basically what you do is you get disorder because of this side-to-side fluctuations. And of course, in principle, you also get this here.
So it sounds like it's bad first. Well, maybe for SPICE it's not as bad within 100% theory, but one consequence of that, for example, would be that if you look at the metallic state, the resistivity would be higher or something like that. This is one of the predictions of your theory.
I'll get to this under this approximate model. But of course, also the average. So here you have an average that lowers your interaction energy. But you also have disorder. That's not good for superconductivity, right? But for SPICE it's not as bad.
It's not just disorder. You make electrons incoherent. Like, because it just has, it's not just disorder, it's the independent disorder. The phonons are vibrating.
But the time scales are different from electronic time scales.
But you also change this on average, right? So you also get an averaged negative contribution.
It's more than that. Okay, well, I don't know. That's a question.
Okay, so maybe I can just go to what we call the phase diagram. So I put phase in quotes here, of course, because that's for the effective model. So this is a sketch. It's a cartoon. It's not a calculation of what we believe happens in this model. So this fluence here pumps this number of bosons that you have. So if you have zero fluence, you basically have the equilibrium case. And there, depending on the value of u, so this is the bare interaction, you have 4 different phases. For very negative U, you have a charge density wave. Then for not too negative U, you have a superconducting state. Then for positive but not too large U, you have a metal. And then for very large U, or large enough U, you cross over into mod insulator. So now when we crank on the fluence, so we put bosons into our system, we create that disorder that we were talking about, but we also create a negative U. And up to a certain fluence, this disorder is irrelevant in the consideration, and the negative U prevails. So there, for these smaller fluences, you would steal away with the charge density wave from the superconductor would steal away from the metal, and the metal would steal away from the mod insulator. But at some point, when the fluence gets large enough, you create large enough disorder such that the single particle levels localize, and that's when you go into an Anderson insulator. So to answer this question, I think that first, for small fluences, the disorder, the effective disorder that you create is not as relevant as the negative U that you create. And then only at large enough fluences, you actually go into an Anderson insulating regime.
So is the result of calculation, or it's your cartoon of what might...
That's just a cartoon. So we're doing DMRG calculations right now. I'll put that in the Outlook, okay? Okay, so now if you try to connect to the experiments, which of course in this simple model is quite difficult. So we already saw in the previous talk that you should probably describe this K3C60 by a 3-band model, and we only have a 1-band Hubbard model, so it's kind of difficult how to map these parameters. But if you just take the bandwidth of that 3-band model and the interaction parameters and the equilibrium superconducting temperature and so on, and just try to map that down naively to a 1-band model, then you end up in a regime where the disorder is still irrelevant to the system, and thus we forget about it in the following. And then you just end up with a negative U Hubbard model with also a band narrowing. And both of these, negative U and band narrowing, depend on time, depending on how many bosons you put into your system. So now solving this negative U Hubbard model is still difficult, so what we employ is just a BCS treatment to that negative U Hubbard model. And because we use this Hartree-Fock-like approximation, we threw away all of the thermalization mechanisms. So to cure that aid effect, we just put in a phenomenological electron decay into the theory. That's just like as if we would couple baths to our electron system, and that just ensures that we thermalize at long times. And also, so far we have treated the phonons to live forever. That's also not very realistic, so what we also put in is a finite lifetime to the phonons, and we choose that as about 5% of their energy, and that just ensures that phonons can leak out of the system again. So this is the pump envelope independency of time, this dashed line here, that we put into the system. And what this pump would do, it would just constantly pump phonons into your system, and if you wouldn't have lifetime in the phonons, it would just stay there forever. But because we put that 5% line width, it just goes back to the equilibrium value. And this translates then to the time-dependent parameters of the band narrowing, which is the red line in this curve here. So it gets more narrow, and then it goes back to the equilibrium result, and also translate to a negative U effect, which reduces this negative U further, and then goes back to equilibrium. So you might wonder why this U is already negative to start with, and this is because we assume that there's some other phonon mechanism that actually leads to effective negative interactions, which we need to do to get this equilibrium temperature of 20 kelvins correctly. Now, in this BCS treatment, what you get is a self-consistent equation for the time-dependent gap, and we solve that self-consistent equation for 4 different base temperatures. This is 15 Kelvin, so below the equilibrium superconducting critical temperature. This is 25, slightly above. This is 50, and this is 100. And this blue line is the solution of the self-consistent gap equation. And if you start in the superconducting phase, then this gap just seems to adiabatically follow these input parameters. But if you are in the phase where initially you have no superconductivity, you need to amplify dynamically exponentially small seed fluctuations in your superconducting order. And that's why you get this sharp rise in this curve here. And then you follow the line of the time-dependent parameter of U and J. Now, as the blue shaded region I also show basically if you take instantaneous values of u and j, so just take instantaneous values of u and j and solve the equilibrium BCS equations, this blue shaded region here is the time regime in which this equilibrium solution would support superconductivity. And you see, of course, because you have to dynamically amplify these seed fluctuations, this blue gap lags significantly behind this blue shaded region here. Now, as a last point, these vertical lines here, so from dark red to yellow, indicate for the next slide the times where we calculated the optical conductivity according to this transiently lived superconducting state. So now we want to talk, because we want to connect to this experimental results, we calculate the optical conductivity in an adiabatic approximation. So the optical conductivity in non-equilibrium, of course, in general depends on two time arguments, the relative time argument and the center time. And we employ this simple adiabatic approximation where we say this is equal to the equilibrium result, which of course only depends on the relative time argument, but evaluate it for a gap corresponding to the gap profile that you saw on the previous slide at the center time. So this is a standard adiabatic approximation. And then you get conductivities that look like this. Here's the real part of the optical conductivity at 25 and 100 Kelvin, and this is the imaginary part of the optical conductivity. So indeed, you find that the real part shows this gap that has some oscillatory in-gap content. This oscillatory in-gap content comes predominantly from the transient nature of the state. So because your state doesn't live forever, you get some in-gap content here. And in the imaginary part, you see this apparent 1/omega divergency. But if you zoom out, then you find some frequency scale where this actually turns around and goes back to 0, which of course is the hallmark of a normal metal. And that's because if you go to lower and lower frequency, you probe longer and longer times. And because your superconductor is transiently lived, at some point you see its metallic nature, and that's when this turns around and goes back to 0. Okay, so with that, I'm done. Let me just go briefly over the summary. So what we propose is a generic mechanism for how phonon drive can change interaction parameters. And I also want to advertise this beautiful recent work by Michael, who's also in the audience somewhere. There he is. And I also want to warn you that there are many open issues. So one is that the value of g that we had to put to get these results that look similar to the experiment is a factor of 2 to 4 too large compared to what we estimated in the beginning. And this could, of course, have the reason that this mechanism has nothing to do with the experiment, or because we naively mapped this 3-band model to a 1-band model. And then more open issues are how does the energy flow between these subsystems, and how does heating work? And for that, we're doing right now DMRG calculations for a 1D system to analyze that. Then another open issue at that stage was, of course, to calculate the non-equilibrium conductivity without this adiabatic approximation. So this we have recently done. And then one big open issue is, of course, the inclusion of other phonon modes. So initially I said that there are many other phonon modes in this K3C6, in this C60 buckyball. And including this is, of course, very important to see how this mechanism that we propose interplays with other mechanisms. And then finally, right now we're also trying to find other materials where maybe you can gain optical control of the mod insulating phase instead of the metal to the superconducting state. All right, that's it.